Hey class, Mr. Henry here with another video lesson. In this lesson, I'm going to be going over some more factoring. We're going to look at a couple special cases. This is actually an example from yesterday's lesson where we were trying to factor this trinomial. So we were looking for two numbers that multiplied to give us 16, but when we added them together gave us -8. We found that the numbers ended up being -4 and -4. They were both the same. So when we wrote out the binomials, we had y minus 4 and y minus 4. At the time I said we could just write that as y minus 4 squared. This is actually a special type of trinomial, what we call a perfect square trinomial, and it has a very specific pattern to it. Here is what that pattern looks like. So there are two possibilities. Either we end up with this a squared plus 2ab plus b squared, or a squared minus 2ab plus b squared. And when we factor them both, we end up with just one binomial squared. In the last example, our b was actually 4. So when we had 4 squared, we had the 16. We had this case in the previous example where we saw that -8. The -8 times 2, the -4 times 2 is why we had that -8 in the expression. So we had something that looked like this. If we are able to recognize this trick when we're factoring, then we can speed it up when we are trying to factor perfect square trinomials, and we don't have to spend some more time trying to figure out what those two numbers are that multiply to the last term but add to the second term. Here are two perfect square trinomials. So if I were trying to factor these, I recognize that they are perfect square trinomials by looking at this last term. So the first thing I notice is this 36. 36 is a perfect square. It actually comes from 6 squared. And I notice that if I have 2 times 6, that gives me this 12. So here I know that I have a perfect square trinomial, and so if I want to factor this, I know that it would just be x plus 6 squared. So if you're able to recognize when you have a perfect square trinomial, you're able to factor just a little bit quicker. Take a look at this second one. In the second one, I've got 25 as my last term, which comes from 5 squared. This term here is -10. That tells me that the number in the brackets must be a negative number. So more specifically, I probably have -5 squared. And 2 times -5 is what's giving me this -10. So if I'm trying to factor this, I could factor it as x minus 5 squared. Here's a trickier question. Which values of b would give us a perfect square? So what value does this b need to be in order to factor as a perfect square? Well, let's look at this last term, actually, the 49. If I take the square root of it, it is just 7. So the 49 comes from 7 squared. And we know that this b term would have to come from 2 times 7. So that means that the b would need to be 14. But there's actually another possibility. We could end up with the case where we had -7 squared, in which case 2 times -7 would have given us -14. So our other answer would be that b could have also been -14. Here we see our second special case. So this is what we call a difference of squares. In a difference of squares, we have a subtraction. That's where the name difference comes from. And we end up with 2 squares. So x squared is a square and 9 is a square, meaning that we can write it as a square of another number. So 3 squared is 9. When we have a perfect square, we end up with an interesting pattern when we try to factor. You might be stuck trying to factor this, but you could also rewrite this in a different way. If I rewrite this as x squared plus 0x minus 9, Now you can see that I'm looking for two numbers that multiply to give me -9, but when I add them, they must be 0, which if you think about for a second might be a little strange, but if two numbers add to be 0, they must cancel out. One's got to be positive, one's got to be negative. So the two numbers that multiply to -9 but add to 0 are just +3 and -3. So this gives us a factored equation of x plus 3, x minus 3. So we actually see this pattern anytime we have a difference of squares. The two binomials will look almost the same, one with a positive term and one with a negative term. So we had x plus 3, x minus 3. And that 3 just comes from taking the square root of the 9. So any difference of squares will look something like this. We've got two squares and they are being subtracted. And we end up with two binomials, one with an addition and one with a subtraction. Let's look at a couple examples. So here we have x squared minus 49. Now that we know how to recognize something as a difference of squares, we can factor it quite easily. We know that this is going to be x plus something, x minus something. And to figure out what that is, all we have to do is take the square root of 49. The square root of 49 is 7. So factored, this will be x plus 7, x minus 7. Now this other one looks a little bit interesting. There's actually a 4 here in front of the x squared. We haven't really seen a lot of terms like that. But if you think back a couple of days to when we were doing common factoring, you might recognize that this second equation can be common factored. Both 4 and 100 are multiples of 4. So I can actually common factor out the 4 and write it outside of the brackets. So I'll have x squared minus 25 in the brackets multiplied by the 4. So what didn't quite look like a difference of squares before looks a little bit more like what we saw in example A. I can leave the 4 out here and I can factor the part that I had in brackets still. I'll have x plus something, x minus something. And again, to figure out what that is, I just take the square root of the second term. The square root of 25 is 5, so it'll be x plus 5, x minus 5. It's important to note that you should be taking the square root of just 25, not negative 25. If you try to take square root of negative 25 on a calculator, you will obviously get an error because no two numbers could multiply to give us a negative. So we would just need to be taking the square root of 25. So that's the second special case for you guys I have today. These are in addition to the factoring that we learned yesterday.